Hello, our group is composed of the students Diogo Tibério, José Montes, Henrique Figueiredo, and also Sebastião Jerónimo. Our group project for storing and retrieving data is based on the aftermath of the Carris crash incident that happened in Lisbon last summer. With this incident, the Portuguese government identified the need to track and also manage the municipal transportation services. And for this reason, our company has been hired to design and manage a relation database as part of an information system that can track the transportation logistics spendings for every local municipality. With this system, we want to provide a view of all the transportation operations at a municipal level so that every logistical cost and also service can be tracked. By the end of this project, our information system will be capable of answering five key business questions. These questions range from high-risk asset analysis, in this case, which vehicles generate the most repair costs and in which municipalities, all the way all up to the network coverage, in this case, which companies serve the most routes and municipalities. For starting this project, we first needed to modulate our database with all the entity tables and the attributes associated with them. Furthermore, and as you can see by this image, we also design the relations between those entities using the crow's foot notation. We want to implement the same thing we did in Draw.io, but right now in MySQL Workbench. To accomplish this, we first need to initialize the schema. In this case, the schema is going to be called city transit and also define the entity tables, their attributes, and also their data types. And if you can see right here, we also define the foreign keys so we can link the tables between them. To now obtain that image of the relation database we created on Draw.io, we just go here to database, reverse engineering. First, the schema is already created. Then we click continue. We just use our root password and then we click continue. We select our newly created schema, in this case, the city transit. And now you can see that we imported our entity tables, the views, and also the triggers that my colleagues are going to talk about later in this presentation. We click execute, continue, and close. And finally, we can see here the database schema with all the entity columns, their attributes, and also the crow's feet annotation between them.
So I'll be going more in depth into the design of our database, specifically what each entity represents and how different entities interact across the database. Starting off, we have the municipality entity. In our system, this represents the client, meaning that it falls upon the municipality to specify its needs by establishing one or more routes and covering them with one or more services. The company entity represents the service provider or the operator, while the municipality defines the what and the where, the company provides the how. So a company will have its own vehicles, it will employ its own staff, and the same company can be contracted for one or more services. We also included a field that specifies if the company is public or not. The service is a formal contract or binding between a municipality and the company. So each service is tied to a specific municipality and is executed by one and only one company. This entity will also contain important information like when will the service start, when will it end, and how much will it cost. And another important remark is that it's directly connected to both vehicles and staff. So this way we know which vehicles in which employees are performing a certain service. Next, we look at the route entity. This basically defines a path within the transportation network. It is established, as I said before, by the municipality and can be associated with one or more services. so the same route can be covered by different service providers. The company workforce is modeled by the employee entity. An employee can only work at one company at a time, but can be assigned to different services. Each employee is uniquely identified by their NIF. There was, however, an important design decision that we had to make that arises from the fact that we want to model specific interactions that only qualified employees can perform, things like driving a vehicle or performing a repair. To handle a specialized workforce, we opted for dedicated tables for drivers and mechanics instead of simply adding attributes to the main employee table. This does make the schema slightly more complex, however, it is a strategic choice for performance purposes. By using separate tables, we avoid the need for constant triggers or queries to check staff members' role every time we log a task. Then we have the vehicle entity, which serves as the primary physical asset for a company. Each vehicle belongs to a company and is assigned to a specific route. Finally, we arrive at the accident and repair entities. When an accident is logged, it identifies the driver, the vehicle, and the route involved. This record then justifies the creation of a repair entry, which will be assigned to one or more mechanics.
The tricks that we use to optimize our queries were index creation, where we create indices to improve the performance of our where or join clause, to avoid full table scans, and to improve our time complexity from O of n, being n the number of values in the column, to O of log of n. We created indices with high cardinality. So we selected column attributes that have a lot of unique values. This is that we created on MySQL workbench. You can see that mostly are on foreign keys of the table, so high cardinality attributes. We created two triggers. We wanted to keep track of the service costs. So we created one trigger. Every time you insert a service, it inserts the service cost and the service on the log table with the respect cost. It updates, it creates another log on the log table to insert the update service cost. Here are our triggers. Our insert trigger, like the professor asked, that every time service is inserted, a value is inserted on our log table. And we also have an update trigger that, like the professor asked, like every update on the service table on the price, it puts also a row on the log table for updating the service costs. Log table triggers are tested here. We made a few updates, and you can see that our log table keeps the service costs and the updates to the service cost. And we also perform a data insertion for the rest of the table.
For this part of the project, we'll be creating an invoice like this one. The invoice will hold all the costs associated with a specific municipality, in this case for Lisbon. The costs can be services, can be accidents, and can also be repairs. To do this, we'll be creating two views. First view is for the head and totals. It will give us the invoice date, so the date the view was queried, and it will aggregate all the municipality data and sum all the services, sum all the accidents, and sum all the repairs. It will then give us the grand total of the invoice. You can also see here in this table below. For the second view, it's for the details, so it will give us a detailed description of each item. An item can be a service, can be an accident, and it can also be a repair. So as we can see here in this table below, we've got the item type, we've got its description, the date it was recorded, and we also have its cost. Once we have these two tables, we will need to export them, and we will import them into our invoice template. So we will import them here. In this case, they are already imported, and then the values will be filled automatically. So in this way, the invoice will be changed dynamically without ever changing its code. In conclusion, we've successfully designed and implemented a relational database for municipality transportation that ensures data integrity and provides actionable reports for a more efficient city.